All right, good morning, everybody, and welcome to the second day of the storage track as part of OCP Tech Week. This morning, we're going to have a few presentations. The first two are going to talk about hard drives and the vibrations that can impact performance and capacity. The second two will talk about head depop and how to deal with drive failures while keeping them in place. We'll then have an open discussion on that, moderated by Matt. And finally, we'll have a presentation on storage observability. Without further ado, Chris Peterson will kick us off this morning. Chris.
Hi, good morning, everybody. Hope you're doing well. I'm Chris Peterson from Dell, and I'll be speaking today about hard drive dynamics and a recent endeavor by OCP to try to commonalize ways of talking about hard drive dynamics, a tool for that, and language around it. So with that in mind, the name of the presentation is Hard Drive Dynamics, Acoustical Sensitivity, and Industry Alignment on Means of Measurement. Kind of a mouthful, but you'll see why in a second. Again, here's the title. There are some links at the bottom, so you can reference these later if you'd like. This is a subgroup of the storage project, and there's also a mailing list there for it. So I use the term hard drive dynamics. It's not a term that has been used very much prior to about 5 years ago. The reason for that is folks tend to refer to it as RV historically over the past 20 or so years. And RV historically refers to how hard drives are disturbed by vibrations of some sort in an enclosure. Or actually, it doesn't even have to be an enclosure. It could just be you're yelling at a hard drive because you're frustrated with it. You've probably all seen the YouTube video where an engineer shouts at a hard drive and the throughput performance drops. So any form of disturbance then we're calling hard drive dynamics because it's not limited to RV. RV is just 3 of the degrees of freedom, and moreover, as the example I just showed gives, acoustics plays a role. We in the industry have therefore started using the term dynamics then instead of RV, because RV is just too limited. You can have linear vibration, rotational vibration, and acoustical contribution. And in fact, not only just RV and LV, but you can have RV in 3 different degrees of freedom and LV in 3 different degrees of freedom. So yeah, the top bullet there says, writing and reading data requires the heads in rotational media to target specific locations on spinning platters. That's a challenge in and of itself, but then you have things outside of the hard drive trying to shake it, right? You might have the case I gave a moment ago, someone yelling at it. You might have fire suppression system as it emits gas to put out a fire. There's a high acoustic signal associated with that. But the most common are the air movers in host enclosures. Air movers can include fans, blowers, anything that moves air. It could even be the air itself that can shake the hard drive. And these get to the hard drive via the enclosure itself. In the case of vibration, the air mover can shake the carrier it's in, and that shakes the usually metal enclosure, and that transmits along the thing that holds the hard drive, and it shakes the hard drive. But, and that's the historical one that has been called RV, where the transmission is lower than about 3 kilohertz. What we've seen over the past about 10 years is that acoustics is the more dominant mechanism. This is mostly, and as I'll show in the next slide, owing to the empirical observation of the physics with regard to acoustics versus vibration. I have a little diagram there at the bottom that shows a little hard drive, the platters in the middle. On the left-hand side, you can see vibration of the enclosure, and it transmits along and reaches the stack of platters. On the right-hand side, you can see I have sound waves indicated. And I say 20 kilohertz. This is not just made up, and it's not just it is coincidental that it happens to be the range of human hearing. Human hearing is also about 20 hertz to 20 kilohertz. The mechanisms are entirely different between how a hard drive hears noise and the way a human ear hears noise. So it is coincidental that it happens to be about 20 kilohertz. It's empirically observed that it goes up to about 20 kilohertz. Are there any questions I can answer on this high level? Okay. So the original type of disturbance of concern, way back when air movers were running at lower speeds such that their acoustics and vibration were lower, was actually both self-induced, meaning the platters in a hard drive are spinning, so they need to be controlled. But also adjacent hard drives, as they're spinning, can impart vibration into the hard drive of interest. So that's the traditional concern, and it's still relevant. You still need to consider how adjacent hard drives are shaking a chassis and thus shaking other hard drives. Things such as mount impedance, which I believe is being discussed in a later session, is important. For example, you might have a chassis that wants to resonate at some of the imparted vibration signals from an adjacent hard drive. But the one we're going to talk about today, and what has led the OCP team to pursue an acoustical surrogate, is the air movers. The air movers continue to increase in speed because the cooling requirements in most enclosures that also house hard drives is going up dramatically. I did also, of course, mention a moment ago fire suppression systems. When they are emitting gas to put out a fire, they emit a high noise content, which can also disturb the hard drive. Obviously, shock events, dropping a computer can disturb the hard drive. And I mentioned the example, the engineer yelling at the disk enclosure. I reference that so often because it's an easy way for folks to get an idea of what this disturbance means. A little bit on the transmitted vibration. I give a little plot on the right-hand side there of actual measurement within a server. And, the vibration amplitude with regards to air movers goes with about the second power of RPM. And the types of things you have to consider there are the fundamental frequency of rotation, given there by F0. That's it's a type of thing as when you're driving your car and you notice your wheel is unbalanced. You'll kind of notice every time the wheel spins over, you'll get a thump with that, right? The same type of thing happens with air movers or even with hard drives themselves. There will be, if it's a little bit off center, you'll get a little bit of a bump each time you rotate or revolve around the spindle. And that's vibration associated with fundamental. And then there's pole pass, and that's related to the magnetic poles in air movers. It is also relevant in hard drives, but the one we're talking about here is air movers. In either case, they both generally scale with about the second power of the RPM of the air movers. Historically, servo systems in the hard drives have been developed in this frequency range. I mentioned that these are generally around up to 3 kilohertz. And the current servo systems in hard drives are generally designed for that range of frequencies and are able to identify the problem frequency and reject it, the amplitude. By reject, I don't mean technically reject, I mean compensate for it. But ultimately, if you only had frequency content in that range, if it was generally controlled, the hard drive could handle it. As I say in the bottom bullet, it works well if there's a finite number, meaning you don't want to have 100 of those spikes because then you can't track all of them. But there's a finite number of them, and you can generally track them, then you can generally reject them or compensate for them. Again, the plot at the right shows some different spikes across the frequency range in vibration content measured at a hard drive. However, acoustics scales with about between the 5th and 7th power of air mover speed. If you remember, I said vibration scales with about the 2nd power of air mover speed, meaning a small increase in speed of the air mover results in a lot more acoustic energy. This acoustic energy is in many forms. The most prevalent, the one that you'll hear if you've got fans and a computer nearby you, is the blade pass tone. Blade pass literally means as the blade's passing a certain point in space, it creates a pulse. And when you have X number of blades, you'll have X number of them passing that point in space per revolution. So the formula for that is number of blades times the fundamental frequency of rotation, as I mentioned in the previous page. Depending on the blade design and the PQ point of operation of the air mover, that can be fairly prominent. You can have if we look at this plot on the right, this is just a sample plot. I'm not referencing a specific chassis or air mover, but you can see right around, let's say 2300 hertz and maybe around 1200 hertz, you can see that spike. That's related to blade pass. And by the way, generally speaking, for both pole pass and blade pass, there will be multiple harmonics of them. So you see it continually trail on off. There'll be, it's integral factors of the blade pass or pole pass. They generally tend to go down in amplitude as you go up in frequency. So blade pass is the one that mostly stands out to folks when you've got your desktop computer and you hear it changing fan speeds. You may hear a little whine with it. That's the blade pass. So that's important because if you remember what I said in the previous slide, if you've got a finite number of spikes and they're low enough frequency, the servo mechanism can fairly well reject it. Pardon me just one second. Another effect is turbulent broadband noise. So, the whole point of having an air mover is to move air, to cool whatever you've got in the chassis. You might have a bunch of GPUs. Maybe you've got a bunch of SSDs. Maybe you have 90 plus hard drives, which all have heat associated with them. But as that air moves by structures, it's rarely nice and laminar. It generally interacts with the structures and becomes turbulent. I'm not going to go into the empirical laws around acoustics related to turbulence, but suffice to say, acoustic energy is generated with regard to the turbulence. And that generally comes across as broadband noise. There are some general formulas for the frequency content, but it's generally broadband. And by broadband, what I mean is it's not just a spike, it occurs in a wide swath of frequency. And then you also have other aspects of acoustics that are challenging. You have amplifications in a chassis. If anybody plays a musical instrument, I play the violin, for example. The way that a violin amplifies sound and actually outputs it is the enclosure itself is intended to amplify characteristics of the string transmission into the volume of space underneath it. Well, that's great for playing the violin or guitar or other acoustic instrument because you're trying to get the sound out. However, in enclosures, they have several of those characteristics also, called modes. Well, those can amplify acoustic frequencies that can be challenging for the hard drive. That's what I mean by sound field amplifications. So all of these effects, which, by the way, tend to scale with about the RPM, fifth to seventh power of the RPM, are more problematic as air mover speed goes up, right? And, presently the frequency range of the servo is not up to 20K. So as you go up beyond where it's capable of, you have content that can't be controlled well. So acoustics, as I think I've just demonstrated, poses a greater challenge than it ever has in the past. And it's just getting more intense as air mover speed goes up. So that in mind, I've got another plot here. This shows two samples of some hard drives. The actual hard drive supplier model is not listed. This is just intended to show some frequency dependence of different hard drives that were looked at as a function of frequency input to the hard drive. The x-axis is frequency, the y-axis is unweighted SPL at the hard drive connector. The point is not to say, hey, concern yourself with these specific SPLs. The point here is to show in the left-hand plot, you can see, up until maybe about 4,000 hertz, I've got, I can go up to high SPL without degradation of the hard drive. However, then you begin to go a little bit higher and you can see around about 5,500 hertz, we might have a dip there, meaning at a lower SPL, sound pressure level, I induce the same amount of throughput degradation. And then when I get to 8,000 hertz, it even looks to drop even lower. This is just showing that the frequency dependency of these sample hard drives here. So, it's very important then for our industry where we're trying to enable folks to be able to use hard drives. There's lots of reasons to pursue hard drives. My intent here is not to convince anyone of the importance of hard drives in our modern world, but they remain very relevant. They will be for many years to come. So the important part is that top bullet. Both system and hard drive designers want for their products to be compatible. It's no good if I design a system and its acoustic output and its vibration output are far beyond what the hard drive can withstand. Equivalently, it's no good if the hard drive that's designed can only withstand a very low sound pressure level. The two can't work together. So compatibility is the key. Over the past several years, members of both the system designer community and the hard drive designer community have begun to develop their own tools to characterize acoustics and vibration in enclosures. That's fantastic. It works really well to talk with between suppliers and on this regard. However, the problem is that it works when you have one system designer and one hard drive designer. But then when you start to say, well, that hard drive designer is working with 3 other system designers, or that system designer is working with several other hard drive designers, you end up with having to translate data many, many times for the same set of either system level data or hard drive susceptibility. So we realized the need to standardize how we talk about this. And thus the OCP Group formed earlier this year to try to standardize on this. We're working towards a common language and a tool. We started in spring of 2020, and we've established 2 phases of this. We're almost complete with our draft standard to submit to OCP for the Hard Drive Dynamics Acoustical surrogate. I should say that's for 3.5-inch hard drive. And I'll show that on the next page. Phase 2 that has been proposed is to add sensors to that same surrogate, meaning I mentioned before, vibration is relevant, transmitted vibration is relevant. Acoustics was our initial push because we understand that that's less understood in the industry, and we wanted to make sure folks started to communicate about that. But as I said, phase 2 is to add sensors to the same surrogate. Here's, in interest of space on the slide, I put information, but it's too much to read through. Let me just suffice to say, the idea is that we're in this OCP group. We've established specifications for the surrogate hardware, locations of the microphone, the type of microphone that needs to be used, the types of analysis. Specifically, we're using 1/3 octave bands for unweighted SPL. Just some background on that. That's a very common analysis technique. I'm not going to go into the details of why 1/3 octave is so popular, but it is. And also, there have been multiple studies that show if you try to go to just one SPL number, the correlation to throughput degradation breaks down significantly. Even 1 octave band breaks down. So 1/3 octave band seems to work well. If you go to narrow band FFT, you find that you can't correlate that either. So 1/3 octave band also seems to be a good balance of sufficiently refined frequency response and correlation. The template for communication is also discussed within the standard that we're assembling. And so these are all the things that we're putting into the document that will be available in OCP. And if I move to, I think, next to the last slide, this is the call to action. As I said, we're near completion of this standard. And the call to action is that we're asking all OCP members to review, first of all, the impact to hard drive dynamics disturbance of acoustics, as we expect this is something not very well understood or known in the industry, but we want to make sure folks are aware of it and planning for it. Again, it's in everybody's best interest to continue to make sure we can use hard drives. And then we also want you to review the hard drive dynamics acoustical surrogate standard that we're putting together so that you can ask questions about it. You can begin to design it, manufacture it yourself, set it up. If you're a system designer, start to use it. If you're a hard drive supplier, begin to characterize with it so that we can begin to dialogue about the acoustical portion and then begin to work on phase 2. I should also note that I and others, including Matt Shumway, did contribute to a 2019 ASHRAE white paper on the acoustical impacts to hard drive performance. I provide a link there. We also contributed to a liquid cooling ASHRAE white paper that is imminent to be released. And there's a section in there on hard drive dynamics impact of air mover speed increase, as well as acoustical experience impact. I think that's my last slide. So I'd like to open it up to questions that you may have on this topic.
And if you're on the Zoom call, feel free to ask them live right now. We don't currently have any questions in the chat window.
Okay, well, very well. We have in this file, we have ways that you can contact the storage mailing list. There's also the storage project page. Matt Shumway is the leader of this effort, and you can contact him directly. Obviously, we're an open forum, so You can also contact other folks on the OCP membership group who's working on the acoustical surrogate for this effort. And we'd be glad to talk with you more about it and help make sure that you know how to use it for efforts in this regard going forward. It's going to be a continuing challenge into the future. So we need everybody to start to standardize on this.
And one other thing to add, in addition to everything that Chris just said, on the OCP calendar under storage, you'll be able to find out when there are meetings on this topic. It'll show up on that calendar.
Okay, well, thank you very much for inviting me in today to speak. And I hope you have a wonderful rest of OCP Tech Forum.
Actually, Chris, I think we just had one question come in.
Sure.
When do you anticipate that this effort will start changing hard drive designs?
So there's two parts to that. I should say design has already been started. Design change has already started over the past several years. I mean, just because OCP is now engaging on this, the engagements among suppliers and system designers has been ongoing. So there have already been responses to this. But so that being said, it's already happening. So I just expect it to continue, and the challenge is just getting tougher. As I said, I can't stress enough that sound pressure goes with the 5th to 7th power of air mover speed, and air mover speed is only going up in at least servers. I would also argue in some storage enclosures also. So it's one that's not going away, and in fact, just getting more challenging. So the design impacts have already been happening, and they're going to continue.
Yeah, I'm just going to jump in there, Chris. I think one of the more important questions there is, when do we start really impacting the design environment of systems as well, right? Because it's very much becoming a collaborative effort between HDD and system designs, because HDDs are constantly putting in things like tri-stage actuation and more advanced controllers to deal with these increasing vibrations as we narrow track pitch to increase capacity. So I think the key question is, how do we move forward together, and how do we improve systems and that vibration environment, as well as improving HDDs to increase that capacity in the future, right, and drive that low cost storage option for HDDs.
Yeah, I reiterate what Matt is saying there. We can't look at it as just one side or the other. Both sides, both the system designers and the hard drive suppliers collaboratively have to address this problem. If one tries to do it, it won't be successful. That's why a key aspect in this OCP effort is the dialogue, how do you do this? How do you communicate between the two different parties in that? I saw another question here. Do acoustics affect SSDs? No, I'm gonna just put it simple, no. There may be ways in which it does, but not in this regard. So to my knowledge, there are no dynamics challenges to SSDs from acoustics or vibration. However, there may be ones, but not in this context that I was discussing here. So far as I know, SSDs are not affected by the types of things we've been discussing. However, I'm sure that as the years go on, we'll find there are ways that there may be, but at present, no.
All right,
Okay.
Thank you so much, Chris.
Yeah, thank you. Really appreciate it.
All right, we should be able to